Hello everyone. So far we have quite familiar with the route stability analysis criteria and what is the basic rules for to gain the stability for any system. Now here in this lecture I am going to discuss about the concept of relative stability. So far we have developed the concept of absolute stability. Now the thing is that, say for example, we have considered one S-plane and two real poles for two different systems. This pole is for one system, say maybe Gs for this system is equal to 1 by s plus 1. That is, the real part of the pole is at -1, and for this system, say Gs is having 1 by s plus 4 transfer function like this, such that the real pole exists at s is equal to -4. So how this gives you the idea about the relative stability and how can it be done with the help of again router analysis that we will discuss here. From the concept of the time domain analysis, we know what is settling time, and we know the settling time is inversely proportional to the real part of the route or real part of the pole positions, right? Say we are considering a simple route conditions, right? So settling time means how fast this will settle to its desired level, right? So if the real part of the route is far away from your origin, this is your origin, say the pole which is having real part -4, definitely the settling time is less. Okay, this is settling time is less. Here settling time is high. Okay, so that means if the system's poles are far away from origin, from imaginary axis, actually to the left hand side of the S plane, you get that system is said to be better stable. Better stable in the sense this stability will come faster. So that is the concept of relative stability. That means we cannot actually determine the positions of the poles in case of Hurwitz criteria by using the characteristic polynomial, but we can say whether all the poles are located to the left hand side of the S plane. For example, we say a system having all the poles, this is S is equal to 0. So Raoult array actually says all the poles on the left hand side of the S plane, that means from imaginary axis. Maybe in certain case we may say that if all the poles can be located, if all the poles can be located to the left hand side of s is equal to -1 instead of s is equal to 0. Okay, so this is the standard form of Raoult array formations, where we can see the poles are located on the left hand side of s is equal to 0 plane, imaginary plane, and maybe in certain case we can derive such that if all the poles can be shifted to the left hand side of s is equal to -1 plane, and the same stability is achieved. So in this case system is stable, here also system is stable. So we can we can conclude that this system is relatively more stable because all the poles are having the real roots less than -1, s is equal to -1, rather than s is equal to 0.5, s is equal to 0. So definitely this system will be much more stable, so relatively better stable than this. Or in certain cases, if it is possible to get all the poles left hand side of s is equal to -2, so see, you are shifting the real part of the pole. So once the real part of the pole is shifting towards the left hand side, you see the value of the real part of the root is getting increased and the stability is achieved. Till that time the system is relatively more stable and settling time will be much less, right? So by using the Raoult array, how this relative stability can be analyzed, that we will take one example and see how this relative stability is being achieved. Okay, so to study the relative stability analysis, what we have considered, one system we have considered with the characteristic equation, that is a third order, s2 plus 7s square plus 25s plus 39 is equal to 0. Now to analyze its relative stability with respect to some positions s is equal to -1. That means what you have to check? You have to check whether all the poles are having real part less than s is equal to -1. That means instead of considering these sections, what we have to consider? We have to consider or check all the poles are lying at the left hand side of the s is equal to -1. Okay, so what you have to do? We have to only just change the value of s to s minus 1, right? So that means s is replaced by s minus 1. If all the poles have to be checked such that the real parts are less than s is equal to -2, in that case the equation of the s plane will be s is equal to s minus 2. Here s is replaced by s minus 1. So the polynomial will be changed like s minus 1 cube plus 7 s minus 1 square plus 25 s minus 1 plus 39 equal to 0. Once you solve this, you get the equations. That is, the polynomial will be turned like s cube plus 4s square. You solve it, s cube plus 4 s square plus 12 14s plus 20, right? So this in turn will give you like this, and by using the root array s cube s square s to the power 1 s to the power 0, you form the root array and you see this is your 1 14, this is 4 20, means 1 5, and 14 minus 1 by 1, that means your 9, and you see this is 5. So what you see, for this polynomial, which is the polynomial which has been shifted by using the expression of the s plane, s is equal to s minus 1, not s is equal to s. So once s is equal to s minus 1, you see what happens. S is equal to s minus 1 means, in original case, if the value of s is equal to 0, that means this is shifted to s is equal to minus 1. That means this position is shifted to this position. So plane equation of the plane has been shifted from s is equal to 0, imaginary axis was there. Here you have shifted the complete plane to these positions. So now the system is again remains stable because all the elements are positive, right? So system is stable. That means if you shift all the real poles of the system to the left hand side of the s is equal to -1, then also the system remains stable. So that means this is better stable. So this is the concept of relative stability, and you can find up to which level this pole can be shifted. Say maybe you can check it with s is equal to -1.5, maybe you can check with s is equal to -2, maybe you can check with s is equal to -3, and see there will be a point where you will get any one of the element will be negative. That means system may be unstable. So once the system will be unstable, you just leave it. That means that real parts of the poles of that system cannot be taken to the left hand side of this. That means up to that level the system can be made stable. That means settling time may be made faster. Okay, the system stability remains same. Here also system is stable, here also system is stable. Maybe to the left hand side of that position also you will get the system also stable, but the system settling time is actually decreasing. For the same system stability can be improved to some extent, right? So that is the concept of relative stability. Now in this lecture again we will find to solve certain kind of problems, okay, where we can see that there is certain parameter for which we can have the stability. That means range of values for particular parameter for which the system will remain stable, and after that system may be unstable, maybe marginally stable. That means the conditional stability. We will analyze the conditional stability in this lecture next week. So here with certain example we will consider the stability which will be called as the conditional stability, right? So conditional stability means, see, a system is considered here. This is your input, this is output, and this is your system, this is feedback. So definitely this is one means unity feedback system, and first of all, to check the stability of any system, we have to go for the Routh array. So Routh array means we have to consider the characteristic equations. So you have to form the characteristic equation, that is 1 plus gs into hs, that is equal to 0. This is your characteristic equation. So from here you can get 1 plus k by s into s square plus s plus 1 into s plus 4 into 1 equal to 0. So that means this will give you s into s plus 4 into s square plus s plus 1 plus k equal to 0, right? So this is your characteristic equations. If you solve it, this will be a fourth order polynomial. You get s to the power 4 plus 5s cube, s to the power 4 plus 5s cube plus 5s squared plus 4s plus k equal to 0. So this is your QS. Now see, there is a parameter k. What is this? This is the system gain which is given in the system. So k. So k is there. So k is not known to you. So k is the system gain which is not known to you. And for different values of k, maybe the system stability may be changed, right? Say for example, if the value of k is equal to, say you say minus 10. So you put the value of k minus 10 here and solve it. Maybe the value of k is equal to plus 100. You may solve it. Maybe the k value is equal to 0. You can solve it like this. That means there is definitely general procedure how you can get or check the value of k for which the system will be stable, for which the system will not be stable, for which the system may be marginally stable, right? So that is known as the conditional stable, because there is certain range of values of k. So range of k for which three conditions may arise. One is system may be stable, system may be unstable, and marginally stable, right? So this we will analyze in this example. So s to the power 4 plus 5s cube plus 5s square plus 4s plus k is equal to 0. We will make the Routh array corresponding to this and finally see how to check the range of k for different stability conditions. Okay. So we see the characteristic equation for the previous system is like this. So sorry, actually there is a mistake. I have not written this is to the 4 in the last part which I have been written in this board. So now correct it, and QS is actually is to the 4 plus 5s cube plus 5s square plus 4 plus k. Now this Routh array we have to for by the similar procedure. See, s to the power 4, this is 1. Next s to the power 2, 5. Next s to the power 0. Here write just k, because k is some constant. Okay, it may be having positive value, it may be having 0, it may be negative value, whatever may be it will be having, it is just k. So considering this k, next this is 5, this is 4, and this is 0. So 1 5k 5 4 0, and I just do the formulations. 25 minus 4 by 5, right? This is equal to 21 by 5 I may call, and next 5k minus 0 by 5, that means k and 0. So 21 by 5 k and 0. By the similar procedure you can find 4 into this, that means 84 by 5 minus 5k divided by 21 by 5. So this is the first element. Next this is 0, this is 0, so this will be all 0. So 84 by 5 minus 5k by 21 by 5. This is the expressions. Next this into k minus this into 0 by this, that means there will be k, 0 and 0. So we are interested about the first column of the Routh array. So we are considering only the first column. Rewrite this expression like this: s to the power 4 s cube s square s to the power 1 and s to the power 0. See, what we are getting? Y 5 21 by 5. This is 84 by 5 minus 5k by 21 by 5, and this is k. Right? That we can get the first column elements like this. Once the first column elements will get, we just remove this, and our aim is to find the range of values for k for which the system is stable. First of all, see, first of all, stable conditions. We want to have the system stable because we are telling, or the system is to be designed in such a way the system is to be stable, right? If the system is to be stable, so what is the condition for stability? All elements positive. See, first case, this is positive, this is positive, this is positive. These are the functions. This is a function of k, this is also a function of k, right? So if this is a function of k, this is also the function of k, so definitely this must be greater than 0 in order to have this element positive, right? So this will be positive only when 84 by 5 minus 5k by 21 by 5 greater than 0, and this will be again positive when the value of k is equal to 0. See? Because the system is to be stable. System is to be stable means all the elements must have to be positive. So positive means there is certain value, this must have to be greater than 0, right? So there are two conditions. From here what will get? 84 by 5 greater than 5k. That means 5k is less than 84 by 5, or k is less than 84 by 25, and k greater than 0. That means the range of k, we are getting the value of k must be greater than 0 or less than 84 by 25, right? So in this range, you see, for the system to be stable, for the same set of problem, we get the value of k is less than 84 by 25 less than 0. This is the range. That means this is somewhere nearly 7 point something. So if the value of k is 8, definitely this will not be stable, right? So k has to be just varied between this range to make the system stable. This is the first condition, right? Next, we will consider the second case. System is unstable. So system is unstable means, second case, system is unstable. So k 84 by 25 less than 0. In this range, system is stable. So automatically, if the k is say is greater than 84 by 25, so what happens? If k is greater than 25, if k is greater than 25, so 84 by 25, see, put here, what happens? You see, 84 by 5 minus 5 into 84 by 25. That means as greater than 84 by 25, we may call it 90 by 25, say, right? So this is equal to 84 by 5 minus 90 by 5, that is minus 6 by 5. So this element is negative, and at the same time, when this value k is greater than 84 by 25, that is gain is made greater than 84 by 25, the element in the first column becomes negative. So the system is unstable, right? So condition for stability, that is stable and unstable situations we have seen. Now we check the condition for marginal stability. That is very important. So last, the third point is that we will check whether the system is marginally stable or not. Number 3, just recollect the concept of stability in marginal stability. in this case, what you have to do, we have to rewrite this route array, complete route array. So we'll write it like you see, that was 1 5k, next was your 5 4 0, next 21 by 5, the k 0, next this is 0 0 and 0 0. See, when the system is marginally stable, then what is the implications on the route array? Means any row, all the elements are 0. Any row, all the elements are 0. Definitely, that is not the last element, last row. We will have to consider any row previous than the s to the power 0. This is not under considerations point. So here you see this, if the value of k is equal to 0 make, then this is not possible to get all the elements 0. So as these two elements are already 0, so you can make this equal to 0. See, if you make 84 by 5 minus 5k by 21 by 5 equal to 0, what happens? This will be 0, this will be 0, and this will be 0. That means your row containing s to the power 1, this all the elements will be 0. If all the elements of a particular row in any case becomes 0, then the system will be marginally stable. So in order to get the marginal stable system, what is the conditions or what is the value of k? That is your 84 by 5 minus k equal to 0. So 84 by 5 equal to 5k. So the value of k will have to be 84 by 25. That means if the system gain is adjusted such a way that you get the value of k is only 84 by 25, then automatically this row will be having all the elements 0 and the system is marginally stable automatically. So system will be marginally stable. The question comes, if the system is marginally stable, so what will happen? There will be oscillations and a frequency. There will be one frequency, which is obvious, right? So there will be one frequency, and that frequency we have to consider, right? So how to consider this? Just forget about this. Now coming to this route array. What is this? That means this row containing s to the power 1, all the elements have become 0, right? Once this has become 0, so you cannot find the next element. So now the route array is incomplete. Now the route array is incomplete according to rule. So if the route array is incomplete, what you have to do? You have to take the previous row of which is having all the elements 0. That means we have to consider this row s square. So that is your auxiliary equations. So what is the auxiliary equations? This will be 21 by 5 s square, because s square row, and k into s to the power 0. So that means auxiliary equation becomes 21 by 5 s square plus k, and we know the value of k is 84 by 5 when this condition is achieved. So this is 21 by 5 s square plus 84 by 25, right? So this is your auxiliary equations, and in order to get the row of s to the power 1 in these conditions, what you have to do? We have to take the differentiations of that s. That means ds is equal to your you see 42 by 5 s plus 0. So you get s to the power 1 coefficient, that is 42 by 5, and this is 0 0. Now you can just solve this minus this by this, equal to your k, right? So now you have solved this, and you see this is your auxiliary equations, and by solving the auxiliary equations, what you get the frequency of oscillations, right? So frequency of oscillation can be obtained by using this auxiliary equations. That means 21 by 5 s square plus 84 by 25 is equal to 0. So s square equal to minus 84 by 25 into 5 by 21. So this is 4 by 5. So minus 4 by 5. So s is equal to plus minus j root over 4 by 5. So you see the marginal marginal stability has been achieved, and the roots have become only the imaginary. So the roots are either here and here. So by considering this s is equal to plus minus j omega, we see what is the frequency of oscillations. You get frequency equal to root over 4 by 5 in radian per second, right? So this is the way how the condition of stability can be achieved. That means there is certain range of values for particular k or some parameter, for which you can get either the system may be stable, maybe unstable, maybe conditional stable, right? And we say we will just get one more example solved in the next class based on this conditional stability analysis. Okay, thank you.